Welcome back to Math 263. In this sequence of videos, we're going to talk about section 10.5 and the comparison test. So specifically, this family of videos is going to talk about the comparison test, and then the next few videos will talk about the limit comparison test. Okay, so the first question we have has to do with the theory of these comparison tests. And the question is, what does a test do for us? Right, the thing that we saw already with the integral test is that a convergence test is telling us, does the series converge or not? And the potential answers it can give us are yes, it can say no, the series diverges, or it can say that it doesn't know the answer, that it's inconclusive. Right, so we also saw this for the integral test and the divergence test. So those were the two other tests that we looked at. Okay, so the idea of the comparison test is to compare our series to a series that we understand. So we suppose that we have two sequences of numbers, the terms an and the terms bn, and we suppose that they are non-negative. Right, so that's going to be an important feature for us, is that the terms are going to be non-negative. And we ask that an is less than or equal to bn. And then here I have some dots, and that's because I want to fill in with the statement that it's true at least for n large. Okay, so then the idea is, if the inequality holds like that term by term, then we're going to have an inequality at the level of the series. And what that means is that if this big one converges, so if this big thing is finite, so the one on the left is finite, sorry, the one on the right is finite, then that forces this one to be finite. That's one way of using the test. Or we can go the other direction, and we can say, well, if the one on the left here is infinite, then the one on the right is infinite. And this is just a simple game of inequalities. And so this is the way the statement is. So that is the theory of the comparison test. Now I have a graphical interpretation of it. Right, so let's say I have here, I'm going to think of this, the blue one is my big one, right? So the blue is the bn's, and then the sort of peach colored ones are my an's. And the fact of the matter is that when n is, when we see here immediately that graphically these an's are less than or equal to, right, term by term, those things are less than or equal to the blue ones. So this top series here converges. Right, that converges by the p-test. Right, it's a p-series for p equals 2. So this guy then, this converges by the comparison. And there we go. That's a graphical interpretation of the comparison test. Okay, we have one other little piece of important theory, which is, well, we need to understand sometimes what happens if a series has terms, some of which are positive and some of which are negative. We're going to see this in a little bit more depth a little bit later on, but for now it suffices to say that if you then replace the series with the absolute value and that thing converges, then the series itself will be forced to converge. Now, the other way around doesn't hold. There are going to be examples where the series itself converges, but the series you get by taking absolute value, that thing diverges. So we'll see a little bit more of that in a later section. But for now, just a useful thing is, if we want to apply the comparison theorem, the comparison test, then, and we have signs that change, it's often useful to look just at the series where we take the absolute values of all the terms. And that'll be good enough to tell us that the thing converges.